Today I'm going to walk you through the basics of using CloudFoil. So when you first log into CloudFoil, you'll see an airfoil on your screen, and on the right hand side is a bunch of settings. And CloudFoil is designed to basically allow you to walk right down each of these settings and submit a case at the end. So I'll just walk down each of these really quickly. So first we have a case name. We can put whatever we want in there. And then we're going to specify the airfoil geometry. There are two different options right now, either a NACA 4-digit or you can read in a custom airfoil. With the NACA 4-digit, put the digits in here and it will update the airfoil on your screen. I'll stick with the 2412 for purposes of this example here. The surface interpolation, we can select either cubic spline or linear interpolation. And basically the surface of this airfoil is defined by a bunch of points, and so this is the interpolation method that CloudFoil is going to use between those points in order to create the mesh later on. So I'll stick with cubic spline for now. We can set the length of the airfoil, and this is in the metric system, so this is in meters. Trailing edge, right now the only option is a closed trailing edge, however that will be changing soon to allow for finite thickness or even flat back airfoils. We can also specify a flap, and so if I put that at sealed, you'll see that it will deflect the trailing edge of the airfoil. We can set the hinge point or the flap deflection here. Again, for this demonstration I'm just going to take the flap off. Okay, so we've specified our airfoil geometry at this point. Now we move on to specifying the condition. We set the angle of attack, the altitude, and also the velocity. And we can specify the velocity three different ways, either by setting the Reynolds number, Mach number, or the actual velocity in meters per second. So I'm going to set this to 3 million. And here we can update the inviscid results, and at this point it's going to take the potential flow solution of this airfoil and tell us the expected lift coefficient and moment coefficient about the quarter chord. And because it's a potential flow solution, we're not going to expect this to be extremely accurate, but it is helpful for getting ballpark estimates. Okay, so we've set the condition, and now we can specify our mesh parameters. The mesh that it's going to build is a C-grid mesh, and so we can set the number of surface cells, which is the surface of the airfoil there, and also a surface cluster parameter. Basically this number goes from 0 to 1. The smaller it is, the more it's going to cluster nodes near the leading edge and the trailing edge of the airfoil. We set the number of wake cells. That's the number of cells from the trailing edge back to the end of the domain here, or the exit plane, and also the length of the wake. So right now that's set at 10 chords. So the exit plane will be 10 chords away from the trailing edge. We also set the radial cells. That's the number of cells going from the surface up to the edge of the domain up here. And also the radial length, again, in chords. We specify the first node spacing. There's three different ways we can set that. Most people will probably use a Y plus value. Right now that's set at 1. So it'll basically estimate the distance here at that Reynolds number and this chord length, the distance that the first cell needs to be off, so that all the points along the surface of the airfoil are at a Y plus of less than 1. Or we can set an actual distance in meters of that first cell, the distance off of the surface there. Or we can also set a cluster definition similar to how we set the surface cluster up here by specifying a number between 0 and 1. So I'm going to leave that at Y plus. It tells me the expected size of the coarse, medium, and fine mesh, and I'll update the mesh. This will take just a minute as it builds the mesh, and this meshing software logarithmically clusters these nodes as it moves away from the surface and away from the trailing edge here. So first I'll zoom in here on the trailing edge so we can kind of see how these things are clustered here. And again, we set the Y plus value at the surface to be 1, so we'd expect the distance here of that first cell off the surface to have a Y plus of 1 in the result. As we zoom out, you can see now that that's a C grid, and most meshing software, when you do an airfoil with a C-grid, it puts a straight line between the trailing edge and the exit plane of the domain here. CloudFoil, though, actually solves a potential flow solution of the airfoil and forces the cut condition at the trailing edge, and then from that it can estimate what this wake is going to look like at this angle of attack. Notice we've already set the angle of attack of this simulation up in the condition settings up there. So we can see that this wake is going to come off satisfying the cut condition, and then it's going to slowly move up at about 5 degrees angle of attack. Now this is really helpful because it allows us, so this software can cluster the nodes along this wake, and those are the regions where we're going to expect the high gradients in the flow. So that should improve the accuracy of our solution. Okay, so we've, one thing I want to point out here on the mesh is that we can now view we're looking at the fine mesh. We can look at a medium mesh or a coarse mesh. And this is really handy for doing grid convergence studies. If we want to double the number of nodes in the mesh, then we can just select whichever one of these meshes we would like to run. Okay, so once we've set the mesh parameters, we go into the settings section here. First thing we have is a flow model, so we can choose to run an inviscid flow, laminar flow, or two different turbulence models, either the Mentor SST or Spillart-Almaris model. Generally, you use the Spillart-Almaris for higher Reynolds number flows and the Mentor SST for lower Reynolds number flows. Okay, so I'm not going to run through all of these settings here. You can these are pretty common settings for most CFD packages, and you can find out more information in the SU2 manual. But I would like to point out the stopping criteria down here. There's 3 different things that will cause this simulation to exit. First, we can set a residual reduction. So this is set at 10 orders of magnitude. As soon as our residuals drop by 10 orders of magnitude, it will exit. Or we can set a minimum residual here of -10. So as soon as we get to e to the -10 in our residuals, then it will exit. Or it will exit from the max iterations here, and I'm going to bump that up to 20,000 for this simulation. So it's monitoring each of these, and it will exit as soon as one of these criteria is satisfied. We can also specify the output format. We can choose between either ParaView or TechPlot. I generally use ParaView because it's free. TechPlot, though, has a really nice interface, so we choose the output format that we'll be looking at these results in. And now we've set the parameters for this simulation, and we're ready to submit the case. Here we choose which grid, the fine, medium, or coarse grid we'd like to run this on. So I'm going to run this on the medium grid, and a run type. Right now we'll just run a single case, but we could also run a parameter sweep. We could set that parameter sweep to sweep over angle of attack, Reynolds number, Mach number, velocity, or flap deflection, and set it to begin, for example, at 0 degrees, maybe go up to 10 degrees by increments of 1 degree. And so this would then kick off actually 11 different simulations, one at each of these angles of attack. For now, though, we're just going to run a single case. We'll set the number of processors. I'm going to drop that down to 12, and a wall time, so probably run within an hour. So now we're all ready to submit. We click submit here. It asks us if we're sure that we'd like to submit, and it will take just a minute while it submits that case. Okay, so the submission was successful, and we'll receive an email with the results, actually a link to the results. So that email, when it comes, we'll just click on the link and it will automatically download those results. Okay, so here I've downloaded the results. It comes in a myairfoil.zip. Double click on that to extract the files. And inside of this, we see quite a few files here. We have an airfoil.pdf. It just gives us the shape of the airfoil. Coefficients, this will show us the lift and drag coefficients as a function of iteration. We can also look at the final pressure distribution, or look at the residuals as a function of iteration. And all of this information is also included in here. For example, the history.csv, if we open that up, We can look at the lift and drag coefficient as a function of iteration. We also have moment, so force and moment coefficients, lift over drag ratio. These are residuals as a function of iteration. So there's a lot of information here in this history file. We also have a surface.csv file, and this file shows us the pressure and skin friction coefficient over the surface of our airfoil. So for example, we can plot pressure coefficient as a function of x. So that's our pressure coefficient. Okay, but probably the most useful thing, or the thing to make the nice pretty pictures, is these VTK files. So there's one for the surface. I'm actually going to look at the one for the flow though, and open that with ParaView. ParaView is free. It's developed at a national lab, and you can download it, and it's really useful for post-processing. So I'm going to open flow.vtk, and here we're looking at a conservative one. I'm going to look at Mach number, for example. So here's what that Mach number looks like. I'll look at eddy viscosity or pressure coefficient. And ParaView, you can find other tutorials online, but basically ParaView is pretty powerful. You can create contour plots, surface plots, all types of things for both 2D and 3D geometries. Okay, one last thing I want to show is an output from the SU2. It's called forces.dat. And this file basically breaks down all of your forces and tells you whether those are pressure forces or friction forces. So for example, the total lift coefficient is 0.68, and pretty much all of that is coming from pressure. Very little of that is coming from friction. However, drag is 0.02, and some of that's coming from pressure, 0.017. 72% of that is from pressure, and 27% is from a friction component. With that, that should wrap up the introduction to CloudFoil. Hope you'll take a minute and check it out, and I hope that it's useful to you. Thanks.